Broadcasting from the commodity capital of the world, Zurich, Switzerland, this is Insider's Guide to Energy.
This edition to Insider's Guide to Energy is brought to you by Fidectis. Go to www.fidectis.com for more information.
Welcome to Insider's Guide to Energy. I'm your host, Chris Sass, and this week we have an exciting show. We're going back to the marine industry, and we're going to find out about marine power again. And my guest this week is Patrik Möller. Patrik, welcome to the program.
Thanks a lot. Great to be here, Chris.
Well, Patrik, I'm excited to be talking about renewables. As you could probably know, our podcast, we spend most of our time talking about renewables. And we've also done a good bit in the marine space. We've talked about tidal. We've talked about floating wind. And now I think we're going to talk about waves today. That's, I believe, what your specialty is.
That is right. Wave energy is what we do in days and nights and most of the time, yes.
So before we get into the topic, it's probably worth introducing yourself to our audience, who you are, what company you represent, and a little bit about yourself.
Great. Yeah, thanks. I'm Patrik Möller. So I am a co-founder and CEO of CorPower Ocean. So CorPower, we are a developer of high-efficiency wave energy technology that allows converting ocean waves into clean electricity. So yes, I guess my own background, I'm an entrepreneur and technologist, very passionate about creating competitive products out of new ideas, and I've been building deep tech startups for all of my working life, you can say.
Well, cool. So another entrepreneur, as you could probably tell from our list of guests, we like that. I'm in the startup phase myself of a fintech, so I can appreciate what it takes to do that. But you're not a brand new company. I think from what I've read, you were around 2012. Is that when you kicked off this current venture?
Exactly, 2011, 2012, we got started. It was actually the inventor, Stig Lundbeck, who was a medical doctor that I was matchmaked with as an entrepreneur. And then we started the company together at that time.
And where is your company headquartered?
We are in Stockholm, Sweden. So we are about 50 people here in Stockholm. And then we have a second biggest site in Portugal, in the town of Viana do Castelo, about 15 people there. So we're a bit more than 65 people now. So probably the biggest operation in wave energy today.
So let's talk a little bit about wave energy. So what I've learned from doing the podcast and being in the energy business is when we do energy transition or renewables, there's no one right answer. I think that the answer is a lot of different components that add up to solve a problem. And so from what I've looked at on your website and from the information you said to me, wave is what you propose to help in the transition. So maybe talk about, where does wave energy fit in?
Yeah, I mean, we've asked us that question for really, what is the role of wave energy and how can we help our customers to have a real value in the future electricity markets? And I think the way most people are excited about our technology, about the overall challenge of, if you say, meeting that supply meets demand at all times of the year. The biggest challenge now to transition towards 100% renewable electricity might not be so much the total amount of clean energy out there. Just solar alone or wind alone would be sufficient if you just look at the annual basis. But to balance the system, make sure that every part of the year there is clean electricity available, intermittency is a big challenge. And there, wave energy comes in with a very complementary and much more consistent, a much more flat power profile compared to both wind and solar, and also some of the other technologies such as tidal.
All right, so this is where my ignorance is going to come out. So I'm a sailor. I spend a lot of time on the water. I spend a lot of time in the ocean. And what I know about waves is it coordinates to the wind. So one of the things I'm hearing you say is this is more stable perhaps than wind. But generally, when there's wind, there's waves, and when there's no wind, there's not waves in my experience. So is my thinking wrong here?
That is a very good point. But the oceans that are the most relevant for wave energy are the large oceans. So we're talking about the Atlantic here in Europe and the Pacific over on the west coast of the US. And on those large oceans, you have weather systems over multiple days that fetch up the energy from the winds into the ocean as waves, and that concentrates the power flow and then smoothens it. So when you've had weather systems over from, let's say, US, Canada, or even Greenland, working up, fetching the wave energy over multiple days, those weather systems may never pass at all the coast of Western Europe. So if we're in Portugal, for instance, there's very little correlation of the wind of the hour or the wind of the day with the waves coming in, because we're working with the big swells. It's the long swell waves that we are converting. It's not the short wind-driven waves.
Okay, so maybe it makes sense. So I appreciate that. Like I said, I figured you would have an answer to that based on the literature I'd read about your solution. But since we're on a podcast and people can't see your solution, can you visualize or talk us through what it is you've built and maybe describe it so the audience understands what we're talking about before we go much further?
Yes. So the wave energy converters that we are developing, it's a buoy floating on the surface. It's moored to the seabed with a single leg mooring system, so it's attached firmly to the seabed. We use a pile to put that one down, and then we have a cable coming from each buoy down to the seabed, and then we connect hundreds up to thousands in the future of these absorbers into arrays so that you can extract energy out of it. The device, it oscillates up and down and to the side, a bit of an elliptic motion with each wave. And what's unique about our buoys, it's a composite structure that on the inside of that, there is the electromechanical equipment that converts the linear motion that the buoy makes into rotation first. And then we have a regular rotating generator that makes electricity out of that, and a cable down from each device to the seabed.
So if I also remember from my high school science days about waves, waves tend to be bigger where the water's shallow, if I remember, because they have some function of the bottom of the ocean or the bottom that they do to get wave height. So what's the depth? And maybe I'm misspeaking. It's been a long time since I've been in high school, but I seem to remember something about waves and depth being related. So what's the ideal depth for this?
Well, the sweet spot depth is between 30 and 100 meters. And you don't want to be more shallow than 30 because then it's hard to fit the devices, as you say. But it's actually not more energy traveling in the waves in the shallower water. The energy conservation is another topic of high school, that you can't create energy. What's coming in the wave motion is what you get to play with. So what happens when they get to very shallow water is that they compressed and get shorter and higher, but they don't actually carry more energy. So we don't want to be in the breaking waves that you see on the surfing areas. We are further out than that. So 30 meters is a good minimum depth, and you can go up to multiple 100 meters as well. It's just that the cost of the moorings and the cabling start increasing a little bit if you get very, very deep.
Okay, so you're building these wave farms, I think, from what it describes. So you've got these low profile kind of buoys that float. What kind of spacing is it? If you had 100 of these, or I don't know how big a farm is, 1,000 of these, I don't know what the size for megawatt or how big the farm needs to be to produce a good return for your investors. How far apart are these? What do they do for navigation and things like that?
Yeah, so the arrays, we place them in clusters of, let's say, 25 buoys per cluster. So that makes 10 megawatts per cluster. So about the same size as a big wind turbine of today. And it's 150 meters between each device. So that's quite dense. So if you look at the ocean space that we use, we get about 3 times as much power per square kilometer as you do get with a typical offshore wind farm. But they are much smaller, each device. So we're talking about a diameter of 9 meters, about 65 tons of material per device, and that produces about 300 kilowatts per absorber. But then we cluster them up in these clusters, and they have one floating collection hub per group where they deliver their energy into, and then we take it out from that one in sizes and chunks about as a big wind turbine of today.
Okay, so you have this cluster. I believe you've already referenced Portugal, so it sounds like you do this off the coast of Portugal, or maybe that was one of your first. I think I saw a video of one of your first prototypes going across and getting deployed somewhere at one point or another. Um, what kind of wave action does it require to generate? Do you need like a 1 foot wave? Do you need like multiple feet? I mean, how much, how big a wave generates energy?
I mean, the cut in wave, if you say comparing it to wind, is about a foot is good, a quarter of a meter is good. That we can start generating small net power. And then we produce full power at around 3.5 meter waves. And then we use a detuning mechanism, very similar to the wind turbine pitching the blade, so that you can stay at full power output where the waves keep increasing even further, but then reducing the loads while we do that.
Okay. And you're also, what I remember reading, and you said this in your intro, that you founded this with a doctor. And a lot of your literature alludes to the heart as a pump. So maybe it's worth talking about what that means and why you talk about that.
Yeah, that's an interesting story. So Stig Lundbeck, who was the original inventor behind this concept, he was a medical doctor, not a trained engineer, but a medical doctor and really a technical genius. He had this technical vision of just see how solutions should work out, even though he was not an engineer. And he was inspired by the pumping principles of the human heart, where the heart has muscles to pump blood in the outward direction, whereas the refilling of the blood doesn't have a muscle. It's stored hydraulically with pressure that pulls it back and refills it. And that was his inspiration. So our wave devices are so that we have something called a pre-tensioning system that pulls the buoy downwards and balance it at the midpoint. And then the wave is lifting the buoy upwards in the wave motion, but then the return motion downwards is by stored pneumatic pressure. And that was the inspiration by the human heart from the beginning.
Well, that's kind of cool. I like that. Like I said, that appeared in the literature. That seemed kind of fun to me. The analogy of the model or where you came up with it. So wave action hasn't really taken the world by storm. I think there's been a number of different models that I've seen and looked at over the years. Some of them less successful than others. So what makes it time for your company now? What's different about what you're doing than previous models?
Yep. So that is very true. There's a lot of smart people and a lot of initiative that's gone into trying to make wave energy a commercial success. And what has been hampering it is mainly two technical challenges. It's to design devices that are robust enough to survive the toughest storms, at the same time generate enough electricity compared to the size and the cost of the equipment to make it a viable business case. And historically, devices have typically either broken in storms or they've just been very large and costly compared to the amount of energy they could produce. So we've dramatically changed that picture by introduction of new type of this high efficiency wave energy converters. And the key innovation that we brought to wave energy is number one, survival in storm conditions. Our devices are designed in a way that they don't react to ocean waves unless we actively control them. So if you just put them out there, if you lose the control system or you lose the grid connection, they automatically fall back into their natural state, which is a protected, transparent state, you can say. The ocean and a wave buoy, they work a bit like a radio receiver and a transmitter. So the ocean is the transmitter of energy through waves at a certain frequency. And our buoys are then manufactured so that they are in a natural frequency, which is completely off compared to anything existing in the ocean. It's much faster. And because of that, it doesn't react to waves. So you can say we've introduced the equivalent of pitching the blades of a wind turbine. That's how the wind turbine protects itself from overspinning in a storm. And every commercial wind turbine has that function. So that's the first innovation and probably the most critical because we can survive any weather without becoming large and heavy. And then secondly, in regular wave conditions, we use advanced control technology that puts the device into optimal timing with each incoming wave. And when you do that, you strongly amplify the motion of the device and thereby the power capture. So in a 1 meter wave coming in, our device moves 3 meters up and down. And that strongly then increases how much energy you can absorb with a given size and cost of the equipment. So in average, we get more than 5 times as much annual energy delivery per ton of equipment that we need to install in the ocean compared to what was possible in wave energy before. So the structural efficiency, it's a huge improvement.
So who's buying and deploying these systems right now?
So we're working with a number of end users, and that's, I mean, our model is one as an OEM. So we're an equipment producer, and we offer the turnkey wave energy farms and also engineering services to customers who are then utilities and independent power producers, usually who will own and operate the farms. So currently, we're working with an Irish project developer called Simply Blue Energy. So they are developing a first pre-commercial farm on the west coast of Ireland called Saoirse. They've also quite big name in floating wind these days. So a few big projects developed and sold to major energy majors around the world, both in Ireland and now in California and so on. In Portugal, we're working together with EDP, the Portuguese utility, and that's on the demonstration of our first full-scale device that is called the C4. And we're also working there to add another 3 devices into an array. So we form a 4-device array here in the coming years in Portugal. And then we have a number of other large energy companies who we do work with, which are not public at this
That's
moment.
fine. Just curious if, so it sounds like your energy is going to grid then. You're not using it to make hydrogen. You're not using it for other things. It's generally going to grid. Is that what I'm understanding?
Well, we are focused very much on a utility scale delivery, so multi-megawatt type of installations. But there is a lot of interest actually also for offshore installations in the oil and gas industry for decarbonizing assets. And that's an interesting market, at least in the transition period, to drive up volumes. And it's a bit less price sensitive than the most grid connected standard utility market. So that's a great one to build volumes in. We're also working in locations, typically islands, and it could be aquaculture as well. Some of these big fish farms around the world, I mean, there are installations these days that require some 10 to 20 megawatt to run the biggest fish farms. So that's also interesting if you say starting entry applications into the market that we are working towards. But in the big game in the end is large grid connected utility scale farms of multiple 100 megawatts up to gigawatt scale in the future.
That makes sense. So you mentioned in your answer that one of the things is maybe hydrocarbon producers or they're offshore. So in my experience from talking to just a few marine industry members, that a lot of their pedigree came from folks that came from the oil and gas industry because they had so much experience in marine energy. Is part of your crew come from that pedigree as well?
Yes, we have several team members who've had roles in oil and gas companies in the past, and several solutions. A lot of the design codes and the experience and the knowledge and the certification rules are written based on learnings that's been done in oil and gas over the years. Some of the corrosion protection that we're doing, the material choices, it's all guided by learnings that have been done and then put into codes by oil and gas, essentially. So it's very helpful.
It seems to be in the whole marine industry, as I talk to folks, that the foundational knowledge seems to come from oil and gas folks that have developed it over the years. So I guess you said that it doesn't take a huge amount of a weather event somewhere, let's say in the Atlantic or another ocean. So do you have AI or some sort of intelligence that helps you predict your production in the future, or do you have meteorologists on your team? How does someone that has one of these wave farms work it into their power, or understand what the load's going to be at a given time and things like that? What kind of software goes with this, or do you have partners that do that?
Yeah, for meteorological prediction, we just use external services. But the advantage there with waves, it's based on historical events. So when the waves hit the coast of the Atlantic here in Europe, as we talked about, it has already been blowing for multiple days over the Atlantic. So you know already what the winds have been. So the predictability of waves is much higher compared to both wind and solar. So you can provide very accurate predictions in at least a day ahead or even 2 days ahead in cases and there's plenty of software available and data on that. We do have quite a few data scientists on our team who just crunch data and also investigate this complementarity and of the power profile and the value of the energy compared to the other power sources.
So, so help me understand then how this plays into a strategy. So you talk, let's say in Portugal or a grid operator, what would a renewable strategy look like, and what component of it would it be wave in your vision?
Yeah, so we think that wave can play a very important role in kind of filling the gaps in the future electricity systems, and that's the kind of work that's typically been done by grid planners and system expansion engineers, and then policymakers who put down how we're going to make sure that we have energy systems and grid that are balanced. And the role here that wave energy can take, let's take an example of Ireland, which has a quite high penetration of wind already. You know, in a windy day today, there is always typically negative electricity prices, and when it's not windy, you have a big gap in the system. And the higher of penetration of intermittent renewables we go to, the more pronounced that challenge is going to be with volatility in the markets. And wave energy can come in, and yes, with the right mix and it's not just wave energy, you need multiple sources, but wave energy is probably it is the largest untapped source of clean energy out there in the world today. So the size of the opportunity is about 500 gigawatts globally, and that's about the same magnitude, 2,300 terawatt hours per year, as all the nuclear capacity of the world today, or all the hydro capacity. So it's a really, really big opportunity, and it's quite global. It's, of course, if you look here in Europe, it's not the Baltic Sea, it's not the Lake of Zurich, where we have the waves that are worth extracting, but it is all along the Atlantic coast of Europe. So you start down in Portugal, Spain, France, up to Cornwall, Ireland, Scotland, Norway. It's fantastic markets in Europe. And in the US, you have the western coast of California, Oregon, Washington State, and so on, which are the prime market, and quite many other places in Africa, Australia, Indonesia, India, and Southeast Asia as well that have good wave resources. Everywhere you surf, essentially, it's a good place to be. But your question on how big part could it play in the energy system, was that your
Yeah,
thinking?
that's interesting. Yeah.
Yeah, so in a good of these spots, let's take either Ireland or California as an example, it could easily do 20%, 25% of the future power need in order to get us to 100% renewables. We've been doing a number of system studies performed by people who only specialize in grid expansion and finding the lowest cost system. If you say, but what brings you to the lowest cost system with zero carbon? And there for California, for instance, it was found that it picked up, I think, 55 gigawatts of wave capacity in California alone in the mix that gave the lowest cost to achieve zero carbon.
So California is always a little bit of not in our backyard is what I've noticed with power strategies in California. So we've had, and I think we talked in the pre-show that you'd listen to the Acker, where they do some offshore wind there. How hard is it to get licensed, and are you competing with the same space that they would put floating wind in, or is this a different, like, are you getting the government agency saying, no, this area is just for wave and this is for floating wind? I mean, I guess that's one question. The second part of that is there pushback, because folks don't want windmills when they can see them, right? There seems to be pushback at times about that. Now, granted, if you're way offshore, you don't really see it anyway, and I think it's less pushback. What kind of pushback are you guys experiencing, or if any?
Yeah, sure. We start the floating wind and
Please.
It's an amazing development, of course, in floating wind. We've seen since the technology became, if you say, bankable, the main technology risks were eliminated by the demonstration of principal power and EDP, which actually was done on the Agusadora site in Portugal, the exact same substation that we're now connecting our devices into in Portugal. So the investment in floating wind since then has just exploded in the recent years, and that's amazing to see. So we hope to come to that same point in 2024 when we have demonstrated a 4-device array and clocked at least 8,000 hours of operation on that and achieved type certification by DNV, which is generally what we need to convince investors that the technical risks are sufficiently eliminated. We hope to see the same kind of explosion in
investments and deployment in wave energy. And what's happening now in floating wind, we think we can also piggyback a lot on, because it's very much the same kind of infrastructure that is needed. At least the electrical export infrastructure is the same. We designed these wave arrays so that they are plug and play compatible with the export infrastructure of floating wind. So typically 33 or 66 kV electricity export device to device in floating wind, and that's what we do out of each cluster. So then you can, several of the customers working with our technology today, developing farms, are looking at the combination of floating wind and wave. You can then have a common export cable and push that electricity from the two power sources into the same cable. So you can have lower capex by the shared infrastructure, and you can sell electricity at a higher value due to the combined profile that has less variability and thereby a higher value in the market. So that's very, very interesting. And I think also project development and the consenting processes that you mentioned, if you start finding places where this is relevant and start developing sites, the extra cost of developing it for some extra clusters of wave energy to put it into the combined array is very little. So you can also reduce the combined DevEx by developing these sites and projects on the same places. Then depth might be slightly different. Some of the places in California, the big offshore wind sites now being made ready for auctions, they typically go quite far out and quite big depth. In some of the cases, you want to branch off the same cable, but a bit closer to shore potentially, because you can save getting closer to shore. You can have shorter access time. You can have a depth which is more suitable and gives the lowest cost for that part of the array. And you asked a question about the objections, and the people don't want to see the devices, which is, of course, very personal. I personally love to see wind devices out in the horizon, but a lot of people don't. And there's usually quite a bit of NIMBY issue of not having it in my backyard. And wave farms, especially big ones, are usually pushed quite far offshore. And one reason is that you then don't see it. With wave devices, our devices, they stick up a few meters from the surface. So you can stay within, let's say, 3-4 kilometers from shore. You don't see them by eye. So you can have a 500 megawatt array 3 kilometers from the shore, and you don't disturb anyone having a fancy house or another thing on the beach to see the view there, which generally makes it much easier to get social acceptance for wave deployments.
Okay, so what I think I just heard you say is, if there's offshore floating wind, you can take advantage of some of the infrastructure, the common infrastructure, to reduce costs. And so even if you piggyback off on the backhaul or the transport, you can connect into the system, even if you're not located in the same depth, but along the same line of sight, you're good. And then what I heard you go on to say is, just recapping to make sure I understood, is the objections are perhaps less because, unlike a floating wind that I can see on the horizon, if I'm sitting on my deck and having a cocktail in my beautiful beach house in Malibu, yours would be lower, and within a few kilometers, it's hard to see or would not see with the native eye, so it's less objectionable. So I heard all that. I guess the other thing that's interesting, so for floating wind, and when you start talking arrays and wind farms and things like that, is how do you do maintenance on these? Do you just have a barge that picks them up? Do you switch them in and out? Do you do them out? There's moving parts from what you described. There seems to be some mechanical elements inside this floating buoy. They're fairly big from what I can tell. So you need to be near a port access to do maintenance. Give me a little bit of help there, how you support these long term. And also, last question, and part of that is, how long do these things live? What's the life expectancy? Is this a 15-year project, a 30-year project? What are these developers speccing in when they've put an array out there for?
Yeah, so we are designing them to have a 20-year lifetime to start with. We might be able to increase that slightly over time, but 20 years is what we're designing all the structures for, and both fatigue life and everything will be supporting that. Then, of course, you have certain planned maintenance intervals. You change some lubricants, some seals, and some wear surfaces. And we have a goal to get to 5-year planned maintenance intervals. But the nice thing with the modular approach that we're taking is that each device in relative to a typical offshore structure, it's still very small devices. You're talking about 9-meter diameter, 65 tons, which is of course a lot smaller than a big floating wind turbines of 200 meters and thousands of tons. It's still big when you have it in front of you in a machine hall. And what we do there is that we tow it out with a low-cost tug or a small work vessel, and we have pre-installed a anchor and pile on the seabed, and there's a quick connect interface on top of that pile, and you have a pull-in line. And then what you do when you arrive to your anchor is that you put that line into the bottom of the wave energy converter, and then the tug drives off, and by the bollard pull of the tug itself, you pull down the wreck, and then there is a mechanical quick connect that locks in and mates the device to the seabed, and also the electrical connection is made automatically by that. So it's a completely surface operated installation or retrieval process. You don't need any divers, and it can be done in, let's say, 30 to 60 minutes per device. So it's the operations and maintenance, assuming that you're like 3-4 kilometers from shore, as mentioned before, you can also use quite small port facilities, not a big requirements on cranes or facility size or draft of the port itself. And that allows usually quite short access distance and thereby access times. So you can go out in half an hour or an hour, you can tow your device out to the site, and then you can have let's say you have a big farm of hundreds or thousands of devices in the future. You can have a rolling exchange scheme where you do a swap. So you service one device on land, you then tow it out with your vessel, you take out the next one to be maintained, and you put in the one that has just been serviced, and then you roll them over time like that. And you can do very low cost maintenance and do essentially any big thing onshore, which is much easier than trying to do big operations offshore.
So is where you would do the rolling swap, is that every 5 years? Is that what you're saying? About every 5 years you would work through the array, and you would do maintenance on them and put them back out as needed if there was a problem intermittently?
Exactly. That's the target to get to. That's what we're designing everything to get to, a 5-year planned swap interval like that. But then, of course, in the beginning, when you're stabilizing equipment and so on, there's much more frequent small interventions needed. So we also have man access inside the device. You can go out with a small rib or a crew transfer vessel and have 2 service technicians that go inside and change a loose cable or a sensor that is failing, or some electrical equipment or anything else. You can also change lubricants and filters and things like that inside the device, actually in the ocean, small things, and do that offshore.
So I guess, one of the things that keeps some renewable technologies from taking off, in my experience, is the cost of energy produced, or the project performance. So I think one of the gates I heard you mention was kind of getting insurable or getting investors' interest. So there was a milestone that sounds like it yet to be crossed, but sounds like you're in sight of that. Is that what I heard? And then the second thing is, how is the commercial viability of building, per megawatt or per, how does this align to alternate choices? I mean, I know it fits a need based on continuity or getting energy at different times from what you described, but it's still going to be judged on what your cost structure is. So how does this line up?
Absolutely. So the first question there on the bankability, I mean, our whole product development process has been designed in order to take wave energy to a bankable product. And we realized when we started in 2011 that this is going to take some time, and we need to be very structured. And due to some part, due to the history of wave energy, which hasn't always been great, there's a big emphasis of really being data driven and really have proof on every point on the performance, on the reliability, and so to build a solid business case. So we established a 5-stage product demonstration process where we started small scale. So we did lots of tank testing in small models, prototypes. We did a lot of bench testing of the inside of the devices. And then stage by stage, we've been then stepping up the size of the equipment, the size of the team. And currently we're in stage 4, which is our first full-scale demonstrator that we call the C4. So that was built throughout the last years. and it has been in dry testing since the early summer. So we've also developed a dry testing methodology where we have a huge test rig in our machine hall in Stockholm that simulates wave loading on dry land inside the machine hall. So it essentially pulls the wave energy converter back and forth, and we can simulate the worst case storm loading from any site of the world. It's a bit like an IKEA tester that tests the chair a lot back and forth. You want to shake it and heat it and make sure you like debug and stabilize the equipment before you bring something into the ocean. So part of our strategy has always been to do a lot of dry testing and stabilize the equipment, find any issues you can find on land before you put something in the ocean. So that's currently where we are with our first full-scale C4 device in dry testing, and that should finish early next year. And by, let's say, March, April, we expect to be installing the device in the ocean in Portugal. And then that will be followed one cycle of learning. That's our first commercial scale single device with 3 more full-scale devices that we call the C5, which will have, some information and learnings from the first one to take us to a fully commercially viable design. And on that one, we're going to clock at least 8,000 hours of operation, get DNV type certification, show exactly how high availability, exactly how much we produce in every wave condition, so that we can provide availability guarantees and performance guarantees to our customers. And when we have that, that brings us then to a bankable product offering. And we expect to be there around 2024, 2025 now. So we will possibly be the first wave technology get to a bankable product offering.
Okay, so that sounds exciting, but it sounds like you're still slightly more than prototype, but you're in early development. So 2024, 2025, what size economy of scale, what size plants, and where do they need to go do you do to meet? Because you're not going to build hundreds of these things probably the way you're building these prototypes. I just assume that you're going to build some sort of a plant or some sort of a production or contract manufacturer. I have no idea, but tell me what you're thinking.
Yeah, exactly. So the first pre-commercial customer arrays that we're looking at there, they're about 10 megawatts. So 25, 30 devices per project. So that's the kind of steps we're scaling up the manufacturing and deployment with. We're doing 1, 3, 30, and then to the hundreds. And then around 2030, we hope to have scale to deliver around 1,000 units per year. But if you look at the economics then and the cost that you asked around before, the interesting part is that from the day one, we've been really guiding the product development to deliver the structural efficiency. In the end, it's the amount of materials and tons of steel and tons of composites and so on that we use that guide how much is it going to cost when you put volume to it and when the economies of scale kick in. And already with the first full-scale device that we have now, we meet structural efficiency. We get more than 10 megawatt hours per ton of equipment out in an annual basis. And that's well in line with 5 times more than anything else in wave, and is well in line with the best floating wind concepts. So when we start scaling up, we're starting a first 10 megawatt array might cost somewhere between 250 and 300 euros per megawatt hour. So everything is quite high cost when you do few of them. And then we need some cycles of learning to improve the design and just get better at doing more with less equipment. And then, of course, just mass manufacturing and getting the economies of scale when you start doing a lot of things the same way in volume. So after having 600 megawatts installed in the market, we expect to be around 60-65 euros per megawatt hour in LCOE. And at that point, we think we can be competitive with other renewables in most markets due to the system value of wave energy that we talked about before.
And so the supply chain to do this, how sustainable is it? You talked about steel and other pieces in there. So it's great that we make green energy if we can make it green. Is the process of creating these devices, how green is that process?
And we're trying to really make that green from day one by design as well. So we're making sure that all the materials that we use are recyclable. We do a lot of LCA analysis, life cycle assessment on the total carbon footprint from both producing the devices, installing them, and then operating through the 20 years of operation as well. And as long I can say, just using diesel engines on the O&M vessels, which you don't hear so much about always in renewable projects, that's a quite terrible thing for the life cycle assessment. Like 25-30% of the lifetime emissions might be done by just the service vessels that maintain and install these devices. So that's not something you want to keep doing, and we really want to go to battery-powered operations vessels for that reason, to keep really low footprint on the operation itself. That's critical, and we think that can be enabled by the quite small size, and that we don't need to be so far offshore, so you can have short transfer times, and that really enables full electrification of the vessels. So that's on the O&M side. If you look at the manufacturing side, we're using steel and composites. The steel, we're hoping to go to clean, green steel in the future. You might have heard in Sweden, there's 2 big projects ongoing for creating clean steel based on hydrogen. So we hope to work with some of these suppliers and do the devices actually with clean steel when we get going in a little bit of volume here. And on the composite side, we're also working to make sure that we use composites that can be recycled over time. You might have seen now that both Siemens and Vestas now have wind blade manufacturing that allows full recycling of the blades, which has historically been a big challenge for composites. But that's now getting solved, and we're also trying to piggyback on that industrial development, which is taking place, to make sure that we have a total product offering which is completely recyclable.
Well, that's pretty cool. I figured you'd have an answer, but I'd be remiss if I don't ask the question. So we've covered a lot of it. What are the biggest hurdles you see? What's the biggest risk of this not taking off? So you're the CEO of a company, you've made a big bet, you've got years of your life, you've got a huge team of people that are very passionate about it. You've got prototypes and things built. You're mostly down the journey. You're getting close to seeing an end game. What are risks that are still out there for you?
Well, I mean, as I said in the beginning, I mean, wave energy has been a technology play. It's really about getting a reliable product that delivers the energy that it needs to do compared to the cost. There we are very confident today. The devices we are going to be putting in, they will survive the worst case storms, and they will deliver the amount of energy. Still needs to be proven, and there's still going to be glitches. Developing these kind of technologies is just a long row of challenges to solve all the time. And but there is no fundamental technical challenge left. Now it's proving it in larger scale. But what we then really need, it's policy to make sure that this is given the chance to scale up to the volumes in a similar way that wind and solar got the chance to scale up, so that the cost could come down. So I mentioned before that at around 600 megawatts, we think we are fully competitive without any kinds of support with wind and solar in most markets. And to get to that, we need a combination of some of these entry market volumes from, let's say, oil and gas, from remote islands, and from maybe aquaculture and other applications that already can be profitable without support. But then we also need some combination of revenue support and some grants from Europe and from countries. So it's very exciting to see now that the European Commission has put a new offshore strategy in place, and there are clear targets now to have 100 megawatts of wave and tidal operational by 2025, 1 gigawatt by 2030, and 40 gigawatts by 2050. We think that should be 100, but we're very happy to have clear targets. And that is what's needed. So we need that kind of drive from policymakers to make sure that it becomes a viable business case for our customers to start developing these first pre-commercial farms. Let's say it starts with a few 10 megawatts, then it goes to a few 50 megawatt farms, and then we get to the first commercial farms that might be 100 megawatt plus, in order to start driving the volumes and get to the economy scale. That's the support that we need.
So I heard you say in our earlier conversation, we talked a little bit about California, just because you mentioned it and I dove onto that. Pretty much the example you just gave right now talked about the European Commission, a lot more European centric. So what's happening on the other side of the pond? Is there an initiative, or you have competitors over there? Or why the initial entree thinking that Europe might be better from the political and the funding point of view?
Yeah, that's a good one. I mean, in wave energy, actually, Europe is the clear leader today. There is the most advanced technologies and companies, and that's due to a lot of investment that has been made both by countries and the Commission. But US is putting a lot of money. DOE is really investing into wave energy at the moment, and it's building good American suppliers as well. So that's very exciting to see. And by the way, I mean, we work quite a bit and are very engaged in building this sector as well. So we need multiple suppliers of reliable and competitive wave energy to make this big. So that we see as very positive. In California, especially, I mean, there you have the CEC, the California Energy Commission, who kind of puts down the targets and also does a lot of the modeling on determining which mixes of energy do we think brings us to the lowest cost systems and how are we going to drive the energy transition. There is the SB 100 bill that forces or has put in actual law that California should go to zero carbon before 2045, is it, I think. And of course, that's a great push. And there is a system in the US and in California called RPS, Renewable Portfolio Standard. And that says that there should be a certain mix of the sources. You might be very familiar with this. And we are yet to see wave energy in the RPS mix. So we really hope that the California Energy Commission and others will see the value of this and also the huge industrial opportunity of building out the supply chain with all those industrial jobs being built. And that puts wave energy onto the roadmap and puts RPS targets for wave energy, which is now happening with floating wind, by the way, which is fantastic.
So, coming out of COP just recently, the conference, were you guys represented there as part of the Marine, and what kind of activity took place at the conference for wave energy?
Yeah, there was quite a bit of different activities, and there's been in UK especially quite a bit of lobbying lately. There is the auction rounds for clean electricity in UK, and there's something called AR4 coming up soon, auction round 4. And there's been a big debate with UK politicians on whether give ring-fenced support, essentially creating a pot of money reserved for ocean energy. And first, it has been suggested for a very long time. There's something called the Marine Energy Council in the UK that we're also part of. And Andrew and Orbital Energy, that was on another episode here, is also a very active player there. And finally, actually this week earlier, there was the announcement now that there has been a pot for tidal energy protected in AR4. So that's a huge step forward for UK. So we will see tidal farms being built. And it was relevant for tidal in this AR4, and for the coming rounds, it becomes relevant for wave energy as well, because you need a already pre-consented project with a site and a grid connection in order to participate in the auction. And nobody has that in wave yet. But in the next auction round, we then hope to see targets for both wave and tidal. But and some of those discussions were very active during COP. I was there in Glasgow for one of the days and participated in a panel together with this Marine Energy Council. And essentially, we talked about the value and the unique role that wave and tidal can play to help to fill the gaps when it's not windy and not sunny, essentially.
So it sounds like we're on the cutting edge. It sounds like we're on the front edge, but as I keep repeating, it sounds like we're getting close to having a viable solution to get there. And we're kind of running up on time, but I do have one more naive question because I'm still trying to understand things. So with climate change or weather events being, 100-year weather events seeming to take place in less than every 100 years, how does that impact? I mean, you've already mentioned that you can destabilize or you can go to the condition where your device can weather hurricanes and other typhoon or other bad event, I assume, from what you described. How does that impact you? Is that good for you? Is it bad for you? Is it an opportunity because of the weather events cause more volatility in the oceans? Help me understand.
Yeah, you're right. It seems like any wave installation that has been historically has experienced the 50-year wave in the first year they installed. That's not what you want to see, obviously. But of course, you want strong motion in the ocean, so you want energetic seas, but you want consistency. So, I mean, what's mostly happening with climate change is probably that the extreme events get worse. And I'm not a climate expert by any means, but of course we study the wave pattern a lot. And there's a big difference in various places of the world on how much variability you have over the seasons and the periods of the year. Take Chile as an example. That's a very flat profile. You have very high resource, but it's almost entirely flat. The year. Take Ireland. That's the highest, one of the very highest resources of the world, but it also has an extreme points in the winter. It has some very, very high extreme waves. So you would like to have the optimal conditions is that it's energetic but consistent. So you don't want to have too big differences between your peaks and your average. You can say, we do protect ourselves by this equivalent to pitching the blade of the turbine by being transparent in storms. So our devices, they work like a low pass filter. You can say you just let big waves pass by without reacting to them. So it doesn't kill us, but if we could choose, we would distribute all the waves completely evenly over the year.
All right. So it just is, it sounds like it doesn't really harm you. You'd prefer more predictability or evenness, but it's just a matter of fact, and it doesn't seem to impact you, is what I'm hearing you say.
Yeah.
So, well, I don't really have more questions. I think we're running up on time. I appreciate your patience with me, because certainly wave energy was a new topic to me, as you can probably tell by my questions, but it sounds very good. I think what I'm hearing is that I should expect to see it living here in Europe. I'd expect by 2024, 2025 to see it in commercial use at some sort of scale. And that you're hoping to ramp up and have that be a much larger element of a renewable strategy as we go down the road. So as we get to trying to hit a 2050 or 2035 goal or something like that, you would expect wave to be a considerable part of that, or some part of that.
Absolutely. We are getting ready to start ramping. And yeah, the timing you're describing, I think it's the right one to start seeing that ramp.
Well, that's fantastic. I want to thank you so much for being a guest in the podcast today. It's been a really enjoyable conversation. Thank you.
Thanks a lot. Thanks for inviting me.
And for our audience, you spent another hour listening to Insider's Guide to Energy. I hope you've enjoyed the conversation as much as I have. If you have, don't forget to share the episode with your friends. And as a shameless plug, please don't forget to subscribe or follow us on our LinkedIn group to always find out what we're doing on Insider's Guide to Energy. Look forward to talking to you again next week. Thank you, and bye-bye.